For the last century, fossil fuels have powered the modern world, driving unprecedented progress and prosperity. And while there may be enough to last another few hundred years at most, accessing those reserves will become increasingly challenging and incredibly expensive. And yet our demand for energy is unrelenting. By 2050, our energy demand may double as the planet's population exceeds 9 billion people. In less than 10 years, the world will have to fuel an additional 2 billion urban dwellers, the equivalent of 7 Shanghais or 10 Londons each year, with each and every one using lights, appliances, technology and transport. The drain on power will be phenomenal, dangerously so. Time is running out for humanity's dependence upon conventional energy sources, and the global energy industry is working frantically to develop cleaner, more efficient technologies. But despite ploughing vast sums into renewable energy research, we're yet to see a viable alternative that is affordable, sustainable, available, and safe. Sadly, of the potential solutions to the current energy crisis, none can compete with the cost efficiency and simplicity of fossil fuels, which account for 86% of the world's primary energy use. That's not to say no one is trying. While renewable energy accounts for just 18% of global consumption, some believe that will grow to 50% by 2050. Today, the most significant alternative fuel sources are nuclear fission and hydroelectric power, followed by geothermal, solar, tide, wind, wood and waste. Unfortunately, each has problems, meaning they may only be part of and not the whole solution. Let's take a look at the options. Nuclear fission produces energy by splitting heavy atoms such as uranium to release the internal energy that holds them together. It's appealing because a golf ball-sized piece of uranium produces as much electricity as 20 train wagon loads of coal, without releasing any polluting gases. A fact prompting many countries to put nuclear power back on the agenda. But while nuclear fission is gaining acceptance for its clean credentials and stable generating costs, its safety risks may stop it ever topping the alternative energy tree. In terms of output, hydropower, which uses the energy in falling water to drive a generator, is a significant energy source, producing 16% of the world's electricity. Experts predict its market share will rise by up to 60% in coming years. But beyond that, its appeal will wane as potential new locations become scarce. And green isn't always good. On the downside, hydroelectric power has displaced millions for dam construction, released methane into the atmosphere from rotting plants, and decimated species of freshwater fish. So, to satisfy our energy needs, we'll have to look elsewhere. For many scientists, that somewhere is up, to the sun. Solar technology can make a substantial contribution to the world's energy use, and small changes such as replacing electric water heaters with solar do have a big impact. But our ability to efficiently harness solar power has a long way to go before it becomes a serious contender to power today's energy-guzzling world. Another of nature's energy supplies comes from wind. Worldwide, wind energy generates as much electricity as Australia uses in a year, and its reach is growing. But wind too has its problems, particularly the fact it's intermittent and therefore not 100% reliable. We need to find a way to fuel our increasingly high-tech lifestyles without harming the planet. The question is, can it be done? And if it could, wouldn't we know about it by now? Amazingly, it can, and we do. The clear solution is not new, nor is it the stuff of science fiction. It's nature's power source, the energy behind the sun and the stars. It's fusion, the simplest, most elegant and efficient of nuclear reactions. Fusion is the process by which lightweight atoms are fused to form heavier atoms, liberating lots of energy. In the end, there's a little less mass than there was at the beginning. And so, using Einstein's equation, E equals mc squared, the difference is energy. Now, research facilities worldwide are honing their techniques in the race to build what would be akin to the first star on Earth. Though their methods may differ, their goal is the same: to construct a power plant which releases sustained, demonstrable fusion energy, enough to bring power to the grid. The trouble is, while scientists have been liberating energy using fusion for decades, doing it in a sustainable way to make it viable has proved difficult. Still, the scientific community believes it is possible, and its promise is tantalizing. A virtually inexhaustible supply of energy which is clean, affordable, efficient, safe, and accessible to all. Let's look at the advantages of fusion energy. It's clean. With no reliance on fossil or fissionable fuels, fusion is one of the cleanest energy sources available, with the capacity to supply the world's energy needs for millions of years to come. It's affordable. Fusion's key fuel, deuterium, comes from the ocean, and the Earth's surface waters contain more than 10 million tons of deuterium, an essentially limitless supply. It's efficient. A fusion power station might consume several hundred kilograms of fuel in a year, compared with millions of tons for a conventional power plant, all without releasing any carbon into the atmosphere. Perhaps most exciting is the fact fusion is safe. Unlike energy released through nuclear fission power plants, no fissionable materials such as uranium or plutonium are used in fusion, which means there is no risk of a meltdown, major accident, or explosion. So, how long have we known about fusion? While scientists have actually been observing fusion reactions for decades, we have understood the process at a subatomic level for well over half a century. From those early days, the fusion race has continued at a rapid rate, with scientists and engineers refining techniques to release energy through high and low temperature fusion for more than 80 years. The result is where we are today, on the brink of the next step in the evolution of energy for the future of mankind. Let's take a look at the different schools of thought in the fusion debate. Hundreds of privately owned and government-funded fusion facilities are trialing different methods. However, three key processes are garnering the attention of the scientific community. Thermonuclear, or plasma fusion, relies upon extreme temperatures of up to 300 million degrees to fuse together particles of deuterium and tritium. The difficulty lies in finding materials capable of handling such intense conditions. Other challenges include fleeting rather than sustained reactions, as well as fusion's nemesis, generating more energy from the reaction than you put in to create it. Countries including the US, China, and the EU have forged a partnership to explore plasma fusion by building the biggest fusion reactor ever made in the south of France. The International Thermonuclear Experimental Reactor, or ITER, is due for completion by 2020, when its advocates hope it will create a reaction generating enough power to supply 500,000 homes. If it does, a commercial fusion power station will follow before the end of the century. Around the world, other key players in the plasma sphere are building test facilities and planning prototype power plants. While in California, scientists are investigating laser fusion, which focuses the energy of huge laser beams to heat and compress a target filled with hydrogen fuel. The scientific community soon hopes to learn whether laser fusion will successfully overcome its challenges to achieve ignition. In the Asia-Pacific region, low-temperature muon-catalyzed fusion is at the forefront. Japanese and UK collaboration, Rick and Rahl, opened a new muon facility in 2008 to conduct experiments using the world's most intense muon beam. In Australia, Star Scientific has established a purpose-built laboratory and testing facility to support its method of producing muons in vast quantities to deliver sustained, controlled, muon-catalyzed fusion. Muon-catalyzed fusion is a well-known scientific process where a subatomic particle known as a muon captures two deuterium atoms, bringing them together until they fuse, resulting in energetic particle release and helium. Historically, its key hurdle has been producing muons in sufficient volumes to make it a viable energy source. When many researchers moved on from muon-catalyzed fusion, thinking its problems were insurmountable, Star Scientific remained focused on perfecting a world-first technique to economically and constantly produce pions, which immediately decay into muons, the elusive catalyst to make muon-catalyzed fusion a reality, just like it happens in nature. The question is, are we still decades or more away from a genuine solution? Star Scientific's Stephen Horvath believes we are closer than we think.
Among the difficulties facing the world scientific community is how to achieve and sustain net energy gain by fusion. The muon-catalyzed fusion we are testing at Star Scientific will occur near ambient temperature and uses very little energy. This makes the energy input versus output scenario irrelevant. Therefore, muon-catalyzed fusion can be considered a very real and viable global energy alternative.
Star Scientific is in the final stages of fine-tuning its technique, meaning fusion power in the mains could finally move from the realm of fantasy to reality.
The achievement of sustained fusion will deliver clean, limitless energy to our carbon-constrained world. Star Scientific's muon-catalyzed fusion solution is leading the charge to provide green, safe and affordable energy to an increasingly power-hungry planet.
If the breakthrough really is this close, it will be a fitting culmination to Star Scientific's long-term commitment to the fusion energy cause.